So 4.7 is applications involving exponential functions. So it's a little bit of word problems, but it's not a lot. We're just trying to look at a situation that you would say, wow, that's growing exponentially. Like, hey, this YouTube channel subscribers growing exponential, like that, like one of those really good examples like that. And yes, everyone should subscribe. So here we go. So we're looking at applications involving exponential functions. So our equations will always look something like this. There'll be a number. We know that there's the base, right? We talked about this last lesson. So the base to the x, that is going to be our model to solve problems involving exponential growth and also decay. So something might actually be getting really small very quickly as well. So things can, and we know that because our graph can either be this way. So we had the exponential growth, wow, so fast, look at all the subscribers, like really fast like that. Or it could be the opposite where, whoa, so small, right? So something like that. Okay, so that's why it's exponential growth or decay. Now, if the base is bigger than 1, it's growth, right? So if you have 2 times 2 times 2 times 2, it'll be bigger than 1, so it's going to be growing. If you have 1.2, 1.2 times 1.2, it's also growth. So anything bigger than 1 will be growing. Anything less than 1, right? So bigger than 1. So I'm just going to write that in layman's terms. So larger than 1. That's kind of what you're thinking in your head. Anything larger than 1 will be growing. Anything smaller, so less than 1, in my head, that's all I'm thinking, kind of my translation, means it'll be decaying. So if it was a half, it'd be half times a half times a half. And it'd be getting smaller, right? So smaller and smaller. X is going to be the number of growth or decay periods. So here, the exponent, this part here, X, is how many times you're growing or decaying, right? So if I say twice, it has 2 growth periods, then that would be times to the power of 2, so you go 2 times 2 or 3 times 3, right? So that's the number of. F of x is the final amount that we have, and a is the initial amount. Okay, the number in front of it will be the initial amount, and we'll talk about that in a second here. So let's take a look at this. It helps with the numbers. If we had over here, we had 560, 1.6 to the power of 8. I want you to be able to calculate this on a calculator first. So I need you to get your calculators out. And then, so get your calculators out. Do that first. Okay, so the way we would look at this is we would say, if I was translating it to this, right? So all the words above. So sometimes the words are too much, right? And the symbols are confusing. So let me translate what I said above here. 1.6 is greater than 1, so I would consider this to be growth. Does that make sense? So when you're thinking about above, so that's a growth of 1.6. 8 is the number of times it grew. So this is the growth number of growth periods, right? So just translating what I said above here. And then 560 would be the initial amount. Why is that the initial amount? The initial amount is when t equals 0, or in this time, that would mean the growth periods would be 0. So if I said 8 is the growth periods, what if I made that 8 into 0? Anything to the power of 0 is 1, so that would take away my exponential, and I'd be left with 560. So then if this was 0, if it was initial, that would be 0. 1.6 to the 0 would be gone. It would be 1. So I'd be left with 560. So that's the translation of what I was saying above. The number in front is the initial amount you start with. This is a growth period of 1, or growth factor by 1.6, and this is how many times it grew. 8 times. 1.6 times 1.6, right? And then look, I did this one. 0.82 is less than 1, which would mean that that is a decay. Does that make sense? Right, so kind of translating the words above to what I was showing here. These guys here, this question here, is not asking you to do any of the growth or anything. It's just asking you to use a calculator. So use calculator. Okay, just use a calculator to find. So this is not really a great question. We don't typically ask a lot of these. If anything, we might ask one of these, but it's just showing us that you know how to use your calculator and can find all that exponent buttons and stuff. So on your calculator, you would go 5, and you can go you can put this all in once. So 560, and you can go bracket 1.6, and then to do the exponent 8, usually there's an arrow up. Most calculators nowadays have an arrow up, so to the exponent 8. And you should be able to do that all in one go, and you don't have to write multiple steps. I don't want you rounding twice. The more rounding you do, the more errors we have, right? So we go equals, and you get this lovely thing. So 24, so this we're going to write down equals 24. I put the approximate sign down. I'm not making you guys do it, but anytime I round something, I put a little dot above. That says I rounded. So 24051. You don't have to copy out the commas. The commas are there so that you can see that there's a space, it's 24,000 there. Don't copy out the commas. We don't tend to put commas. And then if I say to the nearest hundredth is... Hundredth is how many? 2 decimals, right? 2 decimals, is that okay? Hundredth? Okay, hundredth is 2 decimal places. So we got 2 decimal places there. And so I want to go 8. And we're always rounding up, right? So 5 and up. So 5 rounds up. Always 5. If it stops on a 5, it rounds up. Does that make sense? Right? I know science has different rules sometimes. For math, we always do, if it ends on a 5, it rounds up. Okay, we know that rule? Okay, so we do that. And here, if we do it again, for this scenario, I'm solving for P. If you're solving for P, we divide. I want you to be able to do this in one go. We're dividing both sides by whatever we're getting rid of. So we're going 0.82 to the 5. And on this part, 0.82 to the 5. I do not want you writing this twice. Okay? So I want one step. You should be able to do this on your calculator in one step and get to an answer. I don't want you approximating 2 times. Right? And I know some teachers in the younger grades want you to show like this approximated, the next approximated, but you're rounding too many times. So that crosses this out, and on this side I get P. Does that make sense? Whatever I'm trying to get rid of, I divide by exactly that. Okay? Then I want you to, in your calculator, going 845 divided by, and then you can go bracket 0.82 or 0.82, 0.82 or 0.82, doesn't matter. Close the bracket, and then to the power of 5, right? I don't want you putting this in twice. Does that make sense? I don't want to have 2 rounds, because you have to round it 2 times, and it actually makes it worse. Okay, and then equals, and I got 220, so 2279.2, round up, 3. I should have done with a 0.5 somewhere. Okay, so okay. And so remember on the side here, 10th is 1 decimal. 100th is 2 decimals, etc. Okay, so we want 2. Is that all right? All right. So now we know how to use our calculator. Let's do some questions. So we're going to take A here. That's my equation. I'm asking you if it is exponential, growth, or decay. Exponential growth or decay. Okay, look here. Where do we look? Yes, growth. We look right here. If it's greater than 1, it's growth. Does that make sense? Okay, so that's an easy one. We like that one. So it's going to be growth. And then I'll put an arrow because we looked here, and it's more. In your brain, you're thinking more than 1. Anything more than 1, it's growth. Good? All right. That's for A. For B, what is the initial population? So I'll do B over here. This is my answer for A. For B, what's my initial population? Initial, and I need you to remember this for always, initial means when t equals 0. Okay, you don't have to write that, but that's your brain. Initial is t equals 0, yes?
Is it 400?
It's 400. So you don't have to show me any work. You can go right ahead, but if you want to see the work, this is what I'm doing. P at 0 is 400, 1.2 to the 0. You don't have to show me that because I'm hoping that you'll go, oh, I know, it's the number in front because this ends up being 1, right? So then that equals 400. And yes, you can go straight to the answer. You would say initial population is 400 frogs. Right? And you don't have to show the work. I'm hoping you'll look at the number in front and go 400 frogs. We are actually going to take off the questions where it asks for time. So when it says when, we're looking for T, question mark, okay? We're going to take that question off. So I'll have to fix the homework. But if you're looking for the time, just because they ask you this year to kind of guess and check, and you're sitting on your calculator just punching in a button. There's a logarithm way to do it. Yeah, and it's just you're going back and forth, and it's just such a useless way, because next year I'm going to say, please don't do that ever again. There's a logarithm. There's a mathematical. There's buttons. There's a formula. Just don't do it. So I'm going to not unteach you. We're just going to skip that question, and next year I'll show you the right way. Okay, there's just no point doing guess and check. Why do guess and check when I'm going to literally say never guess and check again? There's a mathematical way. There's a process. There's the opposite of an exponential, and we'll learn that next year. So anywhere we're looking for t, no guess and check. We're not putting it on the exam, so you don't have to ask it. We're not putting it on the test. We won't ask you to find the time. We'll ask you next year when we show you how to find the time in a good way. Right, in a proper mathematical, not guess and check, yeah. Okay, so C, gone. So when it says when, I'll try to go through the homework and fix it, but I might forget. So, but when it says when, we're not going to ask you the when. But D we can do. So D we can do. D is determine the population in 10 years. So in 10 years, we're looking for just T equals 10. Right? And we're looking for P equals question mark. You don't have to write this, but that's your brain. You're looking, I'm looking for the population when T equals 10. We're going to use our proper writing method with functions. I don't want you just putting Y equals. I gave you the formula. It's P. So you're going to write P at 10 and put the 10 in there. Okay, P at 10. And you can go ahead and just sub that right in. Okay, but please write the proper formula, right? Don't put P at X. Don't put P at T. You're going to put the T in, and they're going to go 400, 1.2, and you're putting the same 10 here that you did here. Does that make sense? So this 10, okay, and no one should be losing any of these marks, right? We taught you this way back in Chapter 1, the proper function notation. So when you put 10 here, you put the 10 in there. Okay, should match. If you put P at T, because some people are still putting P at T here, and they put 10 here. But you should match it, right? If I put 10, then you sub in 10, and then we're going to calculate that. And I want this all in one go. I don't want little steps. And I know sometimes in the younger grades, they say, show us this, show us each. I want this one go. I don't want you rounding twice, because then you're getting more error mistakes from rounding it twice. So 400, and this will be bracket 1.2, and then look for your arrow up button to the 10 and give that to me. So I'm getting approximately, now it's frogs. So I'm going to go with a whole frog, no half frogs, no partial frogs. Yeah, let's round down, right? So realistically, you kind of go, I should not probably round up. I mean, we can be proactive and say, well, that frog survived, but also it's a frog, so it's sad, but I'm going to have to round down, right? Makes sense? I know it's 0.7, however, I can't really, okay. So I'm going to go 24, 7, 6, and then you can say rounded down since frogs. Right? So we technically should be rounding up. I don't know what the book does, but I don't feel good. Like, how do you round up when it's a frog? It's a 0.7, right? So you can say, and I would accept that, and like, oh yeah, you did. That makes sense. You rounded down. Okay? Because you rounded down. So I did round down, and then do a sentence, population in 10 years, right? It's kind of weird. Is 2, 4, 7, 6 frogs. You can let me know what the book does on situations like this, but I can't round up. It doesn't make sense to me. So I would just say, yeah, I know it's right. So I said right here, just do a little explanation, and then that covers it. I think numerically you should round up 0.7, but nah. Any questions with that? Yes. I guess not. No, you can just leave it. Yeah, so I would accept 2, but then, yeah, and if you want to round down, because mathematically it rounds up, I would say I rounded down because it's frogs. Yeah, so, and I would accept 2, 4, 7, 7, because mathematically we're supposed to round up. I just think that logically you kind of go, seems a little weird. But yeah, I would accept both then. Okay? The nearest frog, that's right. All right. Yeah, so I'll put that down. Or 2, 4, 7, 7 frogs. I guess you could be optimistic and you'd be like, you know what? I'm an optimist. 0.7 of a frog is still a frog. Okay? So I know, but that one's kind of weird. And the instructions sometimes would say round down or something, or I would just make sure that the number was lower than a 0.1, and then we'd all have to round down. Right? When we make the question up, we might be like, meh, we'll just change the question. Okay, good. Should I start? I think I'll do a new video just